Somewhere in your daily life, you probably cross a bridge built between 1955 and 1975. You probably don't think about it. You trust it the way you trust the sidewalk. But if you knew what the engineers who designed it actually knew when they drew up the plans, if you knew what they built into the lifespan estimates, what they understood about how long it would last, you might grip the steering wheel a little tighter. In 2007, a bridge on Interstate 35W in Minneapolis simply fell into the Mississippi River during evening rush hour. 13 people died. 145 were injured. The bridge had been rated structurally deficient for years. It was a beam bridge. It was built in 1967. It was 40 years old. In bridge years, that's barely middle-aged, if it had been the right kind of bridge. The right kind of bridge doesn't collapse after 40 years. The right kind of bridge is still standing after 2000. And we know this for a fact, because some of those bridges still exist. The Pont du Gard in southern France was built by the Romans around 19 BC. It's still there. The Alcantara Bridge in Spain was completed in 106 AD, in the reign of the Emperor Trajan, and it still carries traffic. The Ponte Vecchio in Florence has been standing since 1345. There are medieval stone arch bridges in England that carry cars today that were built when the Black Death was still a recent memory. These aren't ruins preserved behind velvet ropes. They're functional infrastructure. And they're all the same type of bridge. They're all arches. So here's the question that should bother you. If arch bridges can last 2,000 years, if the Romans figured out a construction method so sound that the structures outlasted the civilization that built them by 19 centuries, why did we stop building them? Why, around 1950, did the most durable bridge technology in human history essentially vanish from mainstream construction in the United States? Why did we replace it with a bridge type that engineers design with a lifespan of 50 years? The answer they give you is technical. Press-dressed concrete changed the economics. Modern beam bridges could span longer distances more cheaply. The interstate system needed standardized designs that could be built at scale. All of that is true. But it's not the whole truth. Because underneath the technical explanation is a set of decisions made by governments, industries, and professional organizations that had very specific financial interests in the outcome. And those decisions are why the American Society of Civil Engineers currently estimates there are more than 40,000 structurally deficient bridges in the United States. Bridges your car crosses every day. To understand what happened, you need to understand what makes an arch work. The genius of the arch is that it turns the weight pressing down on it into lateral force, outward compression that pushes into the foundations on either side. There's no tension in a true arch. No part of the structure is being stretched or pulled. The stone or concrete is only being squeezed, and stone and concrete can handle compression almost indefinitely. This is why Roman arches haven't crumbled. Compression doesn't fatigue the material the way tension does. The arch is not fighting gravity, it's redirecting it. It is, in the most literal sense, a structure that gets stronger under load. The more weight you press onto a properly built arch, the tighter the stones lock together. There is no failure mode built into the physics of the arch itself. A beam bridge works on an entirely different principle. When you put weight on a beam, the top of the beam compresses and the bottom of the beam stretches. That stretching, the tensile stress, is where beam bridges get into trouble. Concrete is terrible under tension. It cracks. So for most of history, spanning any significant distance with a beam required either enormous mass, huge, thick, heavy concrete or stone or metal, which could handle tension but corroded and fatigued over time. Neither was especially practical for large-scale bridge building. For hundreds of years, if you needed to cross a significant gap, you built an arch, or in some cases a suspension bridge for the very longest spans. The arch was the workhorse of civilization. What's often forgotten is that America itself had a golden age of arch bridges, and it extended right up to the moment the switch happened. The Hellgate Bridge over the East River in New York, completed in 1916, was at the time of its opening the longest steel arch bridge in the world, and so massively overbuilt that engineers predicted it would stand essentially forever. The Bayonne Bridge connecting New Jersey to Staten Island, finished in 1931, stole that record and held it for nearly half a century. The Sydney Harbour Bridge in Australia, opened in 1932, used American steel and American engineering principles, and became one of the most recognized structures on Earth. These were not modest engineering achievements. They were cathedrals of metal, deliberate acts of overbuilding, designed with safety margins so generous that the engineers were essentially building for geological time. The engineers who designed the Hellgate Bridge calculated its structural capacity and then multiplied by factors that assumed truck traffic far heavier than anything that existed when the bridge was built. They weren't designing for the present. They were designing for whatever the future might bring. That tradition, that instinct toward permanence and overbuilding, was alive in American engineering as recently as 1932. And then, in the space of a single generation, it was gone. Then, in the late 1920s and 1930s, a French engineer named Eugen Freyssinet developed and perfected prestressed concrete. The idea was elegant. Before the concrete sets, you run high-tension steel cables through the structure and stretch them under enormous tension. When you release them, they squeeze the concrete in exactly the right places, essentially pre-loading the beam so that when weight is applied, the compression from the cables counteracts the tension that would otherwise crack the concrete. The result was a beam that could span distances previously only achievable by arches, and do it with much less material, much less weight, and much faster construction. Freyssinet's patents became widely available after World War II. American engineers and construction firms adopted prestressed concrete rapidly through the late 1940s and into the 1950s. And for the first time in the history of construction, you could span 100 feet or more with a relatively slender, prefabricated beam that could be manufactured off-site, trucked to the location, and lifted into place in a day. Compared to building an arch, which required elaborate temporary wooden or steel centering to support the structure while it was being built, skilled labor to place the stones or pour the concrete precisely, and weeks or months before the arch was self-supporting, the beam bridge was dramatically faster and cheaper in the short term. This is the moment the trajectory changed, and in isolation, it might have been a reasonable technical evolution. But it didn't happen in isolation. It happened simultaneously with one of the largest public infrastructure projects in American history, and that timing determined everything. In 1956, Eisenhower signed the Federal Aid Highway Act, launching the Interstate Highway System. The plan called for over 40,000 miles of limited access highway connecting every major city in the country. Every highway crossing a river, a valley, a railroad, or another road needed a bridge. And there were thousands of them. The Bureau of Public Roads, the federal agency responsible for the design standards, made a decision that would quietly shape American infrastructure for the next 70 years. They standardized. They developed a catalog of approved bridge designs, and those designs were predominantly beam bridges and box girder bridges, structures that could be designed by formula, fabricated by industry, and assembled by construction workers without specialized knowledge of arch geometry or centering techniques. The reasons were real. Standardization reduced costs. It made quality control easier. It allowed the program to move fast, and speed was the entire point. Eisenhower had partly justified the interstate system as a national defense necessity, the ability to move troops and equipment rapidly across the country. That framing required urgency, and urgency required simplicity. The arch was not simple in this context. Every arch is to some degree a custom design, fitted to the specific span, the specific load, the specific geology of the foundations. You can't take an arch design off a shelf the way you can specify a standard prestressed concrete beam. But here's what the Bureau of Public Roads knew and chose not to weight heavily in their calculus. A standard beam bridge, designed in the 1950s with the materials and methods of that era, had an expected service life of around 50 years. They knew that. The engineers knew that. It was in the design documentation. They were building a national infrastructure system with a 50-year expiration date baked in. And they did it anyway, because the upfront numbers worked. Think about what that means. When they built the I-35W bridge in Minneapolis in 1967, they built a bridge they expected to last until roughly 2017. It fell down in 2007, 10 years early. But even if it had lasted to its design life, that's a structure that required replacement after 50 years. The Romans built bridges 2,000 years ago that still don't need replacement. We built bridges 50 years ago that are currently collapsing. Somewhere in that gap is the real story. And the story gets darker when you look at who benefited from the standardized beam bridge program. The prestressed concrete industry was a beneficiary. The structural steel industry was a beneficiary. I-beam bridges used enormous quantities of structural steel, and the post-war American steel industry was the most powerful in the world and well-connected in Washington. The large civil engineering firms that specialized in beam bridge design were beneficiaries. All of these actors had relationships with the Bureau of Public Roads. All of them were represented in the committees and advisory bodies that shaped the design standards. None of them had a particular interest in arch bridges, which required different materials, different skills, different contractors, and, crucially, generated far fewer repeat contracts. Because they lasted so much longer. An arch bridge that stands for 500 years requires maintenance but doesn't require replacement. A beam bridge that requires replacement every 50 years generates a new contract, new engineering fees, new material orders, new construction work, every half-century like clockwork. If you were a civil engineering firm in 1955, what kind of bridge was better for business? The answer wasn't even close. And the people setting the national design standards were, in many cases, the same people whose firms would be designing the replacements decades later. There's a specific piece of this story that almost nobody talks about, and it involves the craftsman. Building an arch requires a centering, a temporary falsework structure that supports the arch from below while it's being constructed, holding every piece in place until the keystone is set and the arch becomes self-supporting. Building a centering was a skilled trade. It required understanding of the arch's geometry, the sequence of loading, the way stresses distribute as the arch nears completion. In Europe, these skills had been passed down through guilds and apprenticeship networks for centuries. In America, there was a thinner tradition, but skilled workers still existed in the pre-war period. Foremen and carpenters who had built centerings on major arch projects before the war carried the knowledge in their hands and their memories, not in textbooks. This is the nature of craft knowledge. It lives in people, not on paper. After the war, those workers aged out of the workforce. The new generation of construction workers was trained on beam bridges, crane operation, formwork for standard rectangular sections, bolt and weld connections, The centering skills were not passed on because there was no demand for them. And once the skills disappeared, they became a reason arch bridges couldn't be built economically. A self-reinforcing cycle that the industry used to justify not building arches, which meant the skills never came back, which meant it remained true that you couldn't build arches economically. The knowledge was allowed to die, and then its death was cited as evidence that the knowledge had never been worth keeping. It is worth noting that not every country made this choice. While the United States was standardizing its way to the 50-year beam bridge, several European countries continued building concrete arch bridges and masonry arch bridges through the post-war period and beyond. Switzerland, in particular, maintained a strong tradition of arch construction through engineers working in the legacy of Robert Maillart, whose reinforced concrete arch bridges from the early 20th century are so structurally refined they look like sculpture. Parts of Central and Southern Europe still build arch bridges today. And those bridges are not failing. They are not being listed as structurally deficient. They are not collapsing into rivers. The same technology, the same physics, the same Roman understanding of compression, alive and performing in countries that chose not to abandon it. Meanwhile, the bridges built in the 1950s, 1960s, and 1970s are now 60, 70, almost 80 years old. They have exceeded or are exceeding their design lives. In January 2022, the Fern Hollow Bridge in Pittsburgh collapsed without warning on the same morning that President Biden arrived in the city to talk about the infrastructure bill. Nobody died, but the symbolism was almost too pointed. The president was there to announce the solution on the very day the problem announced itself. In 2021, a fracture in one of the steel girders on the I-40 bridge over the Mississippi River near Memphis forced a closure that lasted weeks and choked river barge traffic at one of the country's most critical commercial waterways. Both of these were beam bridges. Both were aging out of their design lives. Both were completely ordinary examples of a crisis playing out on thousands of bridges simultaneously. The American Society of Civil Engineers, in its most recent infrastructure report card, estimated that the backlog of needed bridge rehabilitation and replacement runs into the hundreds of billions of dollars. Every year, thousands of bridges are classified as structurally deficient, meaning they have conditions that require monitoring and limit their load capacity. Some of those bridges carry school buses. Some carry hospital supply trucks. Some carry commuter trains. The most recent federal infrastructure legislation included roughly $40 billion for bridges. That sounds like a lot, until you understand that replacing a single major bridge can cost several $100 million, and there are thousands in the queue. The mathematics never closes. And it never closes precisely because we chose, 70 years ago, to build infrastructure with expiration dates instead of infrastructure that lasts. Compare that to what it would have cost to maintain the arch bridges we didn't build. A properly built masonry or reinforced concrete arch bridge requires periodic repointing of mortar, inspection, cleaning of drainage systems. It does not require structural replacement. The maintenance costs over a century are a fraction of the replacement cost of a beam bridge at the 50-year mark. The long-term economics of arch bridges are overwhelmingly superior. The engineers in 1950 were not unaware of this. The data from Europe was available. The Roman precedent was obvious. They knew. They chose the cheaper upfront option anyway. And they chose it in a context where the people making the decision were not the people who would be around to pay the bill. The engineers and bureaucrats who standardized beam bridge design in the 1950s were not going to be alive in 2007 when the I-35W bridge fell. The politicians who celebrated the interstate highway system as a triumph were not going to be in office when the infrastructure crisis arrived. The choice was made by people whose careers would be over before the consequences began, and the consequences have arrived. Right now, on bridges you cross every day. There is something else buried in this story. Something harder to quantify, but important to name. The Arch Bridge represented a philosophy of building. The Romans and the medieval builders and the great bridge engineers of the 19th century weren't just solving a structural problem. They were building things meant to outlast them. The Arch Bridge was a form of confidence in the future, a statement that the civilization doing the building expected to be here in 100 years, in 500 years, and wanted to leave something worthy of the span of time. When you build something to last 2,000 years, you are placing a bet on human continuity. The beam bridge era replaced that philosophy with something else entirely. It replaced permanence with throughput. It replaced the idea of building for posterity with the idea of building for the budget cycle. It said that the future was someone else's problem, and that the goal was to get the road open as fast as possible at the lowest possible upfront cost. That shift was not just technical. It was a shift in what infrastructure meant, what building meant, what a society owed to the people who would come after it. That is the truth they buried in 1950. Not a conspiracy in the sense of secret meetings and shadowed agreements. Something more mundane and more insidious. A set of financial incentives, institutional choices, and professional decisions that collectively eliminated one of the oldest and most proven engineering traditions in human history, replaced it with something profitable and temporary, and left the people who came later to deal with the ruins. The bridges are falling. The bill is coming due. And the question worth asking, the question nobody in the room wants to ask, is whether we're making exactly the same kind of decision today.